Yo, I hope you're all doing well, except for my enemies. Just kidding, I don't have any enemies. Um, this is a video where we are going to go through the first part, as you can see on top, probability part 1. We will be going over the first part of probability. And by probability, to be more specific, I mean grade 12 or matric probability. This is probably something that if you are watching it at the time of the upload or a few weeks from the upload, in preparation for term 3, if you are a matriculant, if you aren't a matriculant, it would be weird that you're watching this video. Or maybe you just like learning new things. Anyway, at this time, you will be getting ready to do this topic, or maybe you've already done it and you have some things that you haven't addressed yet. Or as I was saying before, maybe you're still about to do it and you'd want a nice introduction. If you're any of those people that I've mentioned, then this video will help you. Now let's get started here. As you can see on the top left corner, we have the word probability in black, and next to it, I have a one-word sentence, or a one-word question rather, that encapsulates what we are trying to do with probability. And what we are trying to do with probability is to put a number, put a value to how likely it is for something to happen. Well, this is a very blanket question because sometimes it gets a bit more specific when we're doing things like counting numbers, when we're doing things like combinations. But for the most part, probability has to do with how likely or unlikely something is to happen. And we're going to start with the revision of these concepts that come with probability, things that we've done from grade 9, I believe. I might be mistaken. Let's say grade 10, up until where you are now in matric. So we said we want to assign a numerical value to how likely it is for an event to happen. And I put the word something just to simplify. We know at both extremes, if something is impossible, we would give it the numerical value 0. And if something is possible or certain, definitely going to happen, it would be 1. Now, an impossible event would be something like living forever, right? So if you say, what's the probability of someone living forever? We would say that it's impossible. So the probability would be 0 because it would never happen. What is the probability of you dying, of someone dying? I mean, at any part in their life, just in your lifetime, someone dies within their lifetime. That's certain. Every person dies. In fact, there is a phrase where they say something about the certainties of life being tax, death, and whatever. Anyway, I hope I don't come off as morbid to you since I'm talking a lot about death. But I don't know, it's the only thing that came to my mind, so don't judge me. Let's talk about the terms that come with probability. The first thing is an outcome. And I would define an outcome, and I'm defining it in my own way. I'm not doing the accredited government approved version of definitions. I'm just doing my own definition that's easy for people to understand, and that's in English, actual English. So an outcome is a way in which something happens. That's the way I am going to define it. It's a way in which something happens, and it can happen in two ways, or we have two different types of outcomes. We can also call an outcome an event. So the two different ways in which outcomes happen, or the two different outcomes that exist, are an event outcome and the total outcomes. We'll give an example of this. Let's talk about the event of tossing a coin. And if we talk about the event of tossing a coin, the possible outcomes that can come from tossing a coin is that it can either land on the head side, or it could land on tails. Those are the two outcomes. Those are the two event outcomes that can happen. Now the total outcomes is head and tails. So it could land on heads or tails over here with the event outcomes, but the total outcomes is heads and tails. It's either one of the two faces or both of the faces are the total outcomes. So heads and tails. So the total outcomes for this event of tossing a coin is two outcomes. Now we know this from, for example, the format of how probability looks, that when we want to talk about the probability of something, and I'm going to use that example that we had before, we'll call it example number 1. So example number 1 over here, when we talk about tossing a coin, we know the format for this would be, okay, I want to say the probability of landing on heads. It would be equal to the event outcome, which is 1. There is only one face with heads on it. And there are two possible outcomes or two total outcomes, so 1 over 2. We also know that we can represent this in different formats. So it can either come as a rational form or the fraction form, which is this, rational. Or it can exist as a decimal, which is going to be 0.5, or it could lastly exist as a percentage. And we know, we've heard the phrase before, there's a 50% chance of this landing on heads, of the coin landing on heads. So these are the different formats in which we can find our probability in: the decimal format, the rational format, and the percentage format. I hope at least until now you start getting this nostalgic feeling that we are going over things that you've done before. I'd even like for you to feel irritated, like, come on, I know this stuff, let's keep on moving. We'll move on. And now let's talk about the next two concepts, which I believe a lot of people confuse sometimes. These are concepts that we use in Venn diagrams, especially union and intersection. So union, you would normally see union, you'd catch it in a question being written as or. So it's something or something, and they would name two events. Here on top, and I forgot to mention this, we're going to define the terms as A and B. So we have two events, A and B, and you can let your imagination run wild what that might be. I'd like for you, just as a suggestion, to associate it with heads and tails. So A maybe could be heads and tails could be B. You could, I don't know, whatever you want to imagine it as. But we're going to be referring to that with our definitions. We say that union is written as A or B. So you normally find it written like this, A or B. And if we had to put a mathematical, a mathematical symbol to it, we would use the word, the mathematical symbol addition or plus. So if we ask for the probability of A or B, you will most likely find it like this, where we say probability of A plus the probability of B. But we'll go over the intricacies of this because it's not always like this. Maybe some of you remember. If you don't, it's okay. We'll go over that. So we say it is written as that. And what this means, if probability of A or B occurring, it means that either both of these things are occurring at the same time. Means either both occur or at least one occurs. So this is what it means when we are talking about union. We know how we'd spot it. Union would be A or B. And if you want to use the set notation, it can also exist as this. I'll show you how it also exists. It can also exist as A union B. So sometimes you might find it like this as well. So that is union. In a Venn diagram, you'd find it like how I've written it down here. We have the two events A and B, and it would be everything in A, everything in B, because we said it's either both. So here's the both, the space between A and B, or at least one, which means it can be one A or it could be both B. So this is the example for union. So we know how it can be written as, how it's spotted. It could be A, U, B, or it could be A or B. We know the mathematical symbol or the mathematical operation. Yes, that was the word I was looking for. The mathematical operation associated with it, it's addition, and it means that both occur or at least one occur. Now let's attach an analogy to this. Let's say we are talking about people playing cricket and playing soccer. Right, so we have some students who play cricket, we have some students who play soccer, and we'll give them a Venn diagram to make this make sense. So, I'm going to give cricket this CR and soccer. I don't know, I sound so American saying soccer. Let me say football. Yeah, that will show the Americans. Football. So who plays cricket and who plays football? We can say that there are 8 students who play cricket. But when we say that, we don't mean they only play cricket. So let me qualify it even more. We say that we have 8 students that play cricket only and 11 students that play football only. And we can say that there are 7 students who play both cricket and football. So if we had to ask once again, as I was saying, if we have to ask what is the probability of people playing cricket or football, as per our definition, it's people who play at least one of them. So I play at least cricket. Someone plays at least football. Or both. That was our definition. We said it is either both occur or at least one occurs. So we covered the at least one, and now we want to cover the both. So the both is 7. So in this case, you can see it's going to be everyone. And the probability of someone playing cricket or football is going to be equal to 26. See, I'm quite good with math. I did that in my head. 8 plus 11 plus 7. I'm quite smart sometimes. Should tell that to my mom. Anyway, let's carry on. Let's move on to our next example. Our next definition. So we're going to talk about intersection now, and intersection would use a different syntax and would look all the more different than what union was. I will use the same wording as I've used before. So it is written as, so we're going to cover the syntax, how it's written, how you see it. It is written as A and B. And if you want an operation that exemplifies or signifies that it is union, then it's going to be what I wrote down here, which is multiplication. And here it means that the events occur at the same time. That the events occur at this, no, let us not say at the same time, or both events are true. That doesn't need to be at the same time, but we can say they both occur. At the same time, I was gonna dig for us a grave there, if I said that. So it says A of A and B, it means that both events occur. Right. So an example of this is what we were talking about, but this time it's only secluded to one region in our Venn diagram. In the Venn diagram before for union, we talked about A or B being whatever's in A, whatever's in B, and whatever's between A and B. In this case, for intersection, it would be when both events occur. And when both events occur, that's that space in between A and B. So in our previous example for cricket, we had 8 students, and you can go back to it because I'm lazy to draw it up again. You can just rewind back to it. From what I remember, we had 8 students that played cricket only. We had 11 students that played football only. And we had 7 students that play both cricket and football. So intersection would just be those 7 students that play cricket and football. Another way in which the syntax might be found, it can also exist as, it exists as A, and this time the sign would be upside down. So A intersection B. Let's move on quickly to more pressing matters, the more important things. Now, these stuff do serve as revision, but it also serves as a nice introduction, a nice icebreaker for us to be able to do what we're about to do next, which are examples that are going to come up. So, mutually exclusive events. And you can see here for mutually exclusive events, and I forgot to add this here. And for dependent and independent events, these are the most important subtopics, because they have a lot of hints, a lot of questions that come with them, and a lot of students that I've had the opportunity to help and teach, they normally have problems with mutually exclusive events and with dependent and independent events, and all sorts of problems. Maybe they have problems identifying if the scenario that's given to them, is it an independent or dependent event? Is it mutually exclusive or not mutually exclusive? Some students even have a problem with saying, sir, why do they use words like mutually exclusive? Why can't they just say what we're going to write down now? And that's where I come in. Well, the answer to that question is sometimes people of maths and science or in the STEM field want to sound fancy. I'm just kidding, obviously. Let's start by defining mutually exclusive events. Mutually exclusive events are the type of events that cannot happen at the same time. So exclusive means it's not available to everyone. Mutual means both things or both parties agree on something. So when you marry these two words together, mutually exclusive, it means that both parties cannot, or both events cannot happen at the same time. We'll talk about what this implies, but before that, let's write down the definition. So we said again, a mutually exclusive event is the type of event. So the type of events that cannot happen at the same time. They cannot happen at the same time. So, what does this imply? It implies a very important thing. Please pay attention to this. What it implies is that the probability of an event A and B, or the probability of an intersection happening, it does not exist. It's not there. It's a fugazi. Right? It does not exist. So we say the probability of A and B happening together, that is 0. Nada. Nilch. Nothing. Is not there. So, how would this look on a Venn diagram? On a Venn diagram, it would look like this. You have A, you have B. That's it. That's how it would exist. That's how it would look on a, on a Venn diagram. We have A, we have B. They don't touch each other. There's no intersection point between them because that doesn't exist. These are mutually exclusive events. So mutually exclusive events can be defined by probability of A or B, but not A and B, because A and B does not exist. Another thing about mutually exclusive events is that when you add them together, so this is another thing, we can add another point. When you add them together, they equal 1 most of the time. I think even all the time, they equal 1 or 100% or 1 over 1. So I'm writing it down in the different formats that we talked about here above: rational, decimal, and percentage. So when you add these together, they are going to equal certain. So how would this happen? Let me give you an example of a mutually exclusive event. We can say that we have a set. Let's talk about a set. Let me use another letter, a set C. And in this set C, we have the numbers. We have the numbers 1 to 6. So we have the numbers 1 to 6, and I'm saying what's the probability of me picking a even number in this set? Well, the probability of me picking an even number, I'm first going to find out how many even numbers I have, the number of even numbers I have. I have 2, I have 4, I have 6. So in these 6 numbers, I have 3 even numbers, 3. And the total amount of numbers I could choose from within this set is 6. So from all of the 6 choices I have, if I want to pick an even number, I have a 3 out of 6 chance, or I have a 50% chance, or I have a 0.5 chance to pick a even number. If I was to pick a odd number, it would be the same thing. There are 3 odd numbers in this set, 1, 3, and 5. So it would be 3 from the 6 that I could choose from. Or again, 50% chance or a 0.5 chance. Now, for us to prove that this thing is equal to, or this is that this event is a mutually exclusive event, we want to say what's the probability of us picking a odd and even number. Now here is where your logical alarms are going to go off, because you're going to say that there's no number that I know of. And if you're watching this, you're in matric. If everything went well for you, you're probably 17 years old. If not everything went well for you, and I wish you well, you're probably 21, or at worst you're 25. But it's okay. You make it there eventually. So if you're 17, you're going to say, in my 17 years of my life, or at least around maybe 12 years of my life that I've been in school, I've never heard of a number being odd and even. So you're going to say, look, the probability of me picking an odd and even, stop pulling my leg here, sir. That probability is 0. And I say, well done. Now you've seen that this event of us picking an even or odd number within the set C, that event is mutually exclusive. It is either I pick an even number. If I don't pick an even number, it's odd. If it's not odd, it's even. If it's not even, it's odd. There's only 2 options. That's why there's no intersection between them. There's no middle ground. It is either black or white. It is either odd or even. But you know, in life, not everything's black and white. There's a lot of gray in our lives, right? I'm not charging you for any of this wisdom that I give you. So I hope this makes sense. We say again that mutually exclusive events are the type of events that cannot happen at the same time. And one of the notes that I've given you is that means that the probability of both events A and B happening, it is 0. There is no intersection point for the event diagrams of the event circles, if that's even a thing. And the second thing, when we add them together, we are going to get 1. And you can see that is proven over here. 3 over 6 plus 3 over 6 is going to give me 6 over 6. And I'm going to get 6 over 6, which is 1 over 1, 100%, or 1, whichever way you want to go about it. The next thing is complementary events. Complementary events. The complementary events, surprisingly, and this is, I was going to say I did this on purpose, but I really didn't. It falls in line with what we did just previously, what we learned about in mutually exclusive events just recently, sorry. I said just recently that if a number, and we talk about this set C with 1, 2, 3, 4, 5, 6 as its elements, we say if a number is not even, it's odd. And if a number is not odd, it's even. And this is what complementary events talk about. We say that complementary events are the type of events that focus on everything but the one event in question. Hey, that's a lot to absorb. But this is the easiest way I could put it. So we say it is the type of event, and I'm going to dissect this. That focuses on everything else but the one event in question. So, what does this mean? Again, we said that we are looking at the set C, and I'm going to explain it using our recent example. And we want to determine what's the probability of us, if we pick a number at random from the set C, that it is odd or even. We say that if I don't want an odd number, so if I say, and this is what the complement of something is, we normally talk about it like this. So we say the complement of odd. So I'm going to write it down here, the complement of an odd number. That's how you would say it when you're talking to your colleague, or you're talking to your teacher, or when you are just talking about the topic of probability to anyone. You would use that phrase, the complement of an odd number. So, and here's how you'd write it down. You would say complement odd, the probability of not an odd number. It can also exist like this, so you can also write it down like this, probability of not odd. So these are the two ways in which you can write it down. We are talking about the syntax. So as I've said before, if you are not picking an odd number, so from these numbers 1, 2, 3, 4, 5, and 6, if I don't pick an odd number, so if it's not odd, it's even. And what is the probability of an even number? It was 3 over 6. If we look at that example for C. Again, if we ask for the complement of an even number, or probability even with that copy here on top, or you say what's the probability of me not picking an even number, I would say if I'm not picking an even number, then I'm picking an odd number. So if I'm not picking an even number, then I'm picking an odd number, and we know the probability of an odd number is 3 over 6 as well. So this is what a complement is. Let's give one more example to learn this home. Another example for odd and even, we can use a Venn diagram. You guys have seen Venn diagrams before. So let's zoom in here. So we have this Venn diagram over here, and maybe here we are conducting a survey to find out what service provider people use. And maybe we're talking about just 2 service providers. We ask people, do you use MTN or do you use that devilish service provider Telkom? So we say do you use Telkom, the devilish service provider? You use MTN, which is not that bad. Can be bad, but not that bad. I mean, we have other ones outside as well, like Vodacom and whatever. So I'll say maybe Vodacom is gonna be in red, and then cell C. Let me just qualify this. The reason why I'm saying Telkom is devilish, because I don't think it has very good network. I don't want you guys thinking there's some conspiracy behind it. They're doing some weird stuff in the basement of Telkom's headquarters. No. I just don't think they have good network. That's all. It's not that deep. So we have interviewed maybe 30 people. We've taken a survey of 30 people, and we find that some people use MTN, and the amount of people that use MTN are 12. And the amount of people, MTN only, and the amount of people that use Telkom, the actual SIM card that goes into the phone, would be, let's say, 5. And the amount of people that use Telkom and MTN, you could maybe think they have a 2 SIM card phone, or maybe they use Telkom as a landline at home, is 3. Then outside, I'm going to have to make all of this add up somehow. 12, 17, and then we say people who use Telkom is 7, and the people who use cell C are 6 people. So here's our whole sample space and the 2 Venn diagrams. I hope this makes sense to you. So if I'm using this example here and I'm saying I want to find the probability of the people who are people of just not devilish stuff, not using this devilish network. So the probability of someone not using Telkom, so we'll say T, and you can put the copy over there. Or you could use another syntax, as I've mentioned to you. You can say P, not Telkom, or not T. Who are the people who don't use Telkom at all? Well, the people who don't use Telkom at all would be the people who use MTN only, the people who use Vodacom, and the people who use Cell C. You've noticed that I've left out the intersection point, and I have to, because these people still are associated with that devilish service provider. So you can't include them in your complement. So it would be people who use MTN only, people who use Cell C, and people who use Vodacom. So it's going to be over here as, what's that? 12 plus 7 plus 6. That is 19 plus 6. 25 out of 30 people use, let's write it down here. 25 out of 30 people, they are using this, they are not using Telkom. And then you can put that in your other formats if asked of you, but normally we want it in the rational form or in the fraction form. Okay, now we're going to leave it there. We're going to leave it there for today. In the next lesson, we are going to talk about dependent and independent events, how to distinguish them, how to separate them, how to find them, and then we're going to look at the formulas for each of these type of events, especially for mutually exclusive events, the general formula for probability, and dependent and independent events formula. And then we're going to start solving some worked examples. I really hope that you've enjoyed this. I know sometimes I can be a bit goofy and sidetrack. I hope you can forgive me for that. If that's something that you do enjoy, maybe I'll carry on doing it. Otherwise, it's really not in my nature to be all gloomy and professional and whatnot. Yes, this is what I've always wanted to say. Like and subscribe. I've always wanted to say that. Like the video, subscribe. If you have any questions, I will try to address you. There's an email in my in the YouTube, the actual channel page. My email's there. Email me, ask questions. I'll try to address them either by writing you an explanation of how you'd solve the question, or just jotting it down on a piece of paper, or maybe I can even make for you a PDF. I'll also make these PDFs available very soon. I won't promise it now, but I'll make them available very soon so that you can refer back to the notes so that they can help you. Anyway, it's been good. I hope you have a good day. Bye.